So I want to go over just a few interesting things about Pascal's triangle. So the first one was, and then once we finish that, we're going to start a little bit on our next topic, which is probability, which you'll see it's some just basic concept that I think many of you have seen before, but we're just going to introduce some of the language behind it. Okay, so this was one of the bonus questions. Bonus number 1. It was, why do powers of 11 show up in Pascal's triangle? Oh, no, yes. The exam was a, if you were not happy with your score from the previous one, and we got to talk about it, and I confirmed that you can, you got the score that you wrote, you didn't have to take it. But if you wanted to, you're always.
Sorry, I was so afraid that I misunderstood you or that I made a mistake. So
no.
Clarifying. Thank you.
Yeah, no problem. Mm-hmm. Okay, so this was one of the bonus questions from the first one. Why do powers of 11 show up in Pascal's triangle? So if you write out Pascal's triangle, you start off with a 1, then you can do 1, 1, then do 1, 2, 1, then 1, 3, 3, 1. And do you guys remember, one way you can get these is listing out all the combinations. So this is like the combinations 2 choose 0. This one is 2 choose 1, 2 choose 2. This is all combinations that are combinations of 3. Then you can also do 1, 4, 6, 4, 1. So just check it out if you have a calculator nearby or just on Google. What are the powers of 11 that you get? So do you guys, what is the first number here? What power of 11 is this? What power of 11 is this one? Anyone know? What power do we need to raise 11 to get 1? Nice. Lily, what did you say there?
I said 0.
Yeah, 11. Anything to the 0 power, remember, is equal to 1. So this is just 11 to the 0 power. How about to get just 11 by itself? Nice. Gabby, what did you say there?
Oh, I said 11 to the first.
Perfect. And then, okay, let's see. Brandon, what do you say about for the second, for this row, 1, 1, 2, 1? What power do we need for 11? Nice, Brandon, yeah, the second power. And then just double check this so you believe it. What's 11 to the third power? 11 cubed is, if you double check it, it turns out to be this. And 11 to the fourth, if you double check, it will be 14,641. So what do you guys think? Is this kind of surprising? Remember how we got these numbers? These numbers all came from like combinations. Does anyone have any explanation why this is? Does this pattern always hold true? Is Pascal's triangle just has to do with powers of 11? What do you guys think? Any theories, any ideas? He really liked 11, yeah. Or is this just some random coincidence? How many of you think it's just some coincidence? Or that, Pascal's triangle is only based on powers of 11. Okay, so let me give you guys a little hint on how to explain this pattern. Anyone want to try it at all? Anyone have any thoughts? Every number starts and ends with 1. Aiden, that's a good observation. Yeah, that's actually really true. Yeah, every number starts and ends with 1. I like that. So there's a lot of things you can do with binomial theorem. In general, let me just kind of show you one example. X plus y to the third power. Can you guys just message me in the chat, what would be the expansion of x plus y to the third power? And we've done this one several times already. And you can use Pascal's triangle if you want. So just message me in the chat. And if you're stuck, if you don't remember, let me know. Well, I'll give you guys just to write it down. And maybe instead of using Pascal's triangle, maybe use actually the combinations. It might be good too. So instead of 1, 3, 3, 1, use 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. Or just take a moment to write down x plus y to the third, expand it out, and then just message me when you're done. You don't have to write it in the chat. Just hit done. Just say done when you're done. Nice, Archer. Excellent. Looks good. All right, we got one student that's done so far. So I'm going to just start writing it out here. But I hope. Do any of you need help working this out? X plus y to the third. Okay, so this would be, first we do x to the third, but then we got to also consider things that have only 2 x's and 1 y, because they always have to have 3 letters. And the number of ways to do that is 3, choose 1. Nice, Gabby. Then we do 3, choose 2, x, y squared. Because the next term will have 1 less x but 2 y's, but we got to put this number in front to count the number of words we can make with 2 y's and 1 x. Because remember, the x of y's can be jumbled up in any way, so we got to count all possibilities. And the last one is just all y's, and that's really 3, choose 3. I'll write it here just for completeness sake. 3, choose 3, and over here is 3, choose 0. But remember that those are just 1. So I'm going to rewrite this underneath. This is going to be 1 x cubed plus 3 x squared y plus 3 x y squared plus y cubed. Nice, Olivia. Excellent. Aiden, great job. Anybody who asked for some help, is that explanation okay? Great. Okay. So this is just the nice thing about Pascal's triangles, if you calculate it, if you actually have all the rows accessible, you can just pull off the row that you need and put it as coefficients 1, 1, 3, 1 in there. Okay. So here's the cool trick, or the useful thing you can do with binomial theorem. We just learned binomial theorem. We did expansion with like different things for x and y. Sometimes to get interesting results, you can actually plug in numbers for x and y. Can anyone think of 2 interesting numbers that you can plug in to try to understand this pattern? There's 2 very special numbers, one number for x and one number for y, that you can plug in that would explain why the powers of 11 show up. Does anyone see what 2 numbers you can put in? I'll give you guys a little bit of time to think about it. what number, like actual like integers, can you plug in for x and y if you want to try to understand why powers 11 are showing up? There's two really, really nice numbers you can plug in. One number for x and one number for y. And it has to do with the number 11. What two numbers are really nice to plug in here? Angel, not a bad try. Gabby, not bad. Not 6 and 5. Try some other ones. I like that, how you guys are thinking. There's something else that does really nice, not 3 and 8. It's something that does really nice with powers. Nice, Angel and Diana. Yes, okay. Let's try out what Angel suggested. Plugging in 10 and 1. Angel, do you want to try to explain what's going to happen when you plug in 10 and 1 into this formula? What is 10 cubed? It's just 1,000, right? So this would just be 1,000. 1 times 1,000 plus 3 times 100. But what about the y? Do we need to worry about the y at all? It's just the 1, so you don't need to worry about it. It doesn't affect anything. And what you notice is that your power of 10 is always just dropping off by 1. So what does that mean for the number? What does it mean when we have a number where the power of 10 that we're adding is just getting smaller and smaller? It just tells us that it's the next digit in the next 10 in the next like place, right? So it tells us that these numbers 1, 1,000, 3 100ths, 3 tenths, and 1 1, these are the digits of our power of 11. 1, 3, 3, 1. What do you guys think about this pattern? Kind of cool? Nice. And you see it works for 11 to the 4th as well. Now, okay, let me ask you guys this. So this is a really, now that you've seen this pattern, it makes sense. Does it always work? Will this work for higher powers of 11? Why or why not? And this really is a question about your understanding of how number representation works. Like if you write 5,678, it means 5,1,678, 5,607 tens and 8 ones, right? So what about the next? What do you guys think? How many of you think it's always going to work? And so hit yes if you think it's always going to work, and hit no if you think it's not always going to work. Okay, we're overwhelmingly yes. We have one no. Does a no want to volunteer to explain what might go wrong? Nice, Diana. That's right. One of the powers of 11 doesn't start with a 1. So let's explore a little bit further. So I'm just going to copy and paste. And I think once you see the next row, you'll see why it doesn't work. So, and we're going to talk about the next pattern in a second. But what is the next row? It's combinations of 5. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, and so forth. And remember this thing, we're going to explain why you can do it in a second. But you can do this thing where, let me copy and paste this, move this down a little bit. Okay, 1, 5. So one thing you can do is you can, to get the next row, we mentioned this earlier, you can add up the two previous numbers above it to get the next number. So 1, 5, 10, 10, because I'm adding 6 and 4, add 6 and 4, and that's also 5, and that's 1. And these numbers we know because they are combinations of 5. This is 5 choose 2, this is 5 choose 3, this is 5 choose 4, and this one is 5 choose 5. This is 5 choose 1, 5 choose 0. But there's this nice pattern that if you ever want to get the next number in the next row, you add the two numbers above it. That's what gets you to the 10. All right. What if we tried to do the binomial theorem with 1 and 10 here? What would kind of be a little bit iffy? Can anyone see why this is no longer the 11 to the 5th power? What's an explanation of why this power breaks down? Nice, Archer, very good. Yes, Lily, excellent. Archer, do you want to say what you wrote there?
I just said because of the 10. I'm not entirely sure actually why though.
Yeah, like in the digit representation, like if you write like what is that, I said 6,782 whatever. You can't have more than 10 of a certain power of a certain place, because that would carry you over to the next digit. So in this case, this 10 here would actually bump you up to be at 1/6. And this 10 here would bump it up to the next level over here. So let's just double check how this would work. 10 plus 1 to the 5th, well, that's going to be a 1 times 10 to the 5th plus 5 times 10 to the 4th. There's still a 1 here. I'm not ignoring it, but it's just doesn't, just a 1. But this is where it gets weird. It's not the next digit. The 10 can't be a digit because it's not a digit. It's a 2-digit number. So plus 10 times 10 to the 3rd, this is going to carry over, this guy is going to carry over 1 spot. So it's actually going to be plus 1. And then plus 10 times 10 squared, this would also carry over 1 spot. This would carry as a 1 over to the next one. So this would be plus 1. And then we have plus 5 times 10 plus 1. So if you want to calculate the next power of 11, it will be 1, 6, 1, let me see, 1, 6, 1. So we have the 1000s. There's no 100 place, 0 in the 100 place, and 5, 1. Nice, excellent, Aiden, very good. So you see the pattern, you can kind of use it, but it breaks down because of the two-digit numbers. And then later there's going to be combinations that are 3 digits, which may mess it up even further. So unfortunately, the pattern holds for the first few, but it starts to break down later after you start getting larger combinations. Okay, are there any questions on this pattern? By the way, what do you guys observe? Oh, yes. It still equals, that is 11 to the 5th, but the problem is like these numbers, you have to be careful kind of how to interpret them as digits. So it technically still like obviously the binomial theorem still works if you plug in 10 and 1, that's not going to stop working. But just this kind of neat pattern that you can just read off the powers of 11 from Pascal's triangle, that stops making sense. So I want to show you one other thing that's interesting to plug in. Do you guys remember that we did this thing where if you add up every row, so if you add this one, you get 1. If you add this one, you get 2. If you add this one, you get 4. 1, 2, 1 is 4. This one, it gives you 8, right? 1, 3, 3, 1. Add them all together, you get 8. And add all of these together, and you get 16. And how about this one? What do you guys get? What do you get if you add all of these together? Nice, Gabby. Excellent. Can anyone explain the reason? This was one of the bonus questions, and I think I talked with you, several of you about it, and we kind of covered it in class. Why is it not surprising that the nth row of Pascal's triangle adds up to a power of 2, 2 to the n? What is the interesting explanation of it? Just a little review. You guys remember what this represented, adding up all of these? It was one of the problems that we did. Yeah, they always multiply by 2. Why is that? What's the interpretation? That's right, nice. Gabby, that's exactly the pattern. Well, why does that happen? And it's related to one of the problems that's from either test. There's one problem that's connected to. And just kind of, I'll focus on the 5th row. Angel, that's right. Angel, can you explain?
There was a problem on both tests asking that you could choose any one of these toppings and you could choose whether to have it or not to have it, meaning that you can either choose or not choose. There's your 2, and
right.
It's to the power of n depending on how many toppings there are.
Exactly. And then what about the other way of looking at it? So that's 2 to the 5th, but why is it also these combinations, which is just the rows? What is this interpretation? If you break it up, instead of doing 2 times 2 times 2, like yes or no, what does this represent? And a few of you answered the question, that one. Yeah, Kanjit, do you want to expand on it? You're basically, right? So for example, if you want to pick the toppings, what combination do we use to count the number of ways to pick no toppings? No toppings is here. 5 choose 0. How many ways are there to get 1 topping? There's 5 ways. 5 choose 1. How many ways are there to pick exactly 2 toppings? 5 choose 2. So it's like kind of like we're counting the same thing, the number of ways you can pick toppings in general, but we're looking at it, we're going about it, each side of the equation is doing it a little bit differently. But at the end of the day, we know that those things are equal because they're counting the same thing. Are there any questions? Hit yes if both ways, if you can understand both approaches, the left side and the right side. Nice. Awesome. And that's a really nice, awesome, great. Okay, I got a lot of yeses, great. So I'm going to show you there's one other way to see why the pattern holds true. I think the way that we just explained it is the most interesting way. It's very intuitive, right? And I think really the insight is once you learn combinations, most people do it this way. This is really a neat insight to say, oh yeah, you can actually come up to each topping and decide I want it or not. That's why there's 32 different ways to do it. But let's look at x plus y again. So can you think of an x plus y you can plug in that would somehow get you to understand this pattern? What numbers can I plug in for x and y that would help me explain this pattern? Just kind of how it was useful to plug in 10 and 11. Aiden, very close, but one number for x and one number for y. What can I plug in to try to explain? So we want to know why, like one explanation we said is we have an interpretation. So we want to know, why is this true? Can anyone see a pair of numbers, one number for x, not 3 and 2, not 4 and 1, just why is 2 to the 5th equal to 5 choose 0, 5 choose 1, 5 choose 2, and so forth? Why is that? How could we come up with an explanation in general for the row of combinations adding up to 2 to the n? And the hint is kind of how I wrote it here. I want to make this somehow look like this. Can you guys think of x and y that would work? Nice, Brendan. What did you say?
And 1 and 1 because 1 plus 1 equals 2, and since it's the power of 5, you just put it in parentheses.
Yeah. Look how it works. It's x plus y to the 5th is going to be x 5 choose 0 to the 5th, 5 choose 1, x to the 4th, y, plus 5 choose 2, x to the 3rd, y squared, 5 choose 3, 5 choose 3, x squared, y to the 3rd, 5 choose 4, it's running out, x, y to the 4th, and the last one is y to the 5th, 5 choose 5. Now, if you plug in x equals 1, y equals 1, then you see that, do you guys agree that the x's and y's, no matter what it is, if it's 1 and 1, those just become all 1s. So the only thing that you're left with is all of the binomial coefficients. And on the right side, we know 1 plus 1 is just 2, so we get 2 to the 5th power. And you can do this for any row and get the same result. Okay? So this is another way of what I mean by sometimes you can plug things into the binomial theorem, actual numbers, and come up with interesting patterns for the coefficients. Okay. Any questions so far? What did you guys think about these ideas of like plugging the numbers in? Do they make sense, this strategy? It's a very neat strategy. Awesome. Okay, so we're going to do one other thing with Pascal's triangle. And this is actually really important. I don't think, unfortunately, most classes, unless it's later in college or something, you don't get to see it too often. But it's really, really easy, and it's really important to understand why. That's always something I think is important. So we understood. Do you guys have a really good understanding of why, like, each row is what it is, where these rows come from? Do you guys feel by now like we know it comes from, what concept? If you had to kind of just say a one-word concept, where does each row come from? What's the one word that explains where each row comes from? What are these numbers? If I ask you to like find the 20th row of Pascal's triangle, what tool would you use? Nice. Kanji, what did you say?
Combinations.
Yeah. All the rows of Pascal's triangle just come from combinations, because that's the number of ways you can make a certain word with 2 letters. Or like pick friends to go to a movie with you. Anyhow, the rows we know come from combinations. But there's this really amazing pattern, which is sometimes used to teach this this pattern, or used to teach Pascal's triangle. And let's say, oh, you don't need combinations, just need to know this pattern, which I think is a little bit misleading, because you don't want to go through, if you want to get something in the 20th row, you don't want to go row by row to get it. You just want to be able to get the 20th row. However, the pattern is really amazing. The pattern is the one that we mentioned, that if you want to get the next row, you can add the 2 numbers above it to get you to the next one. I'm sure there's some golden ratio stuff. Off the top of my head, I don't know where it is, but I'm sure there's golden ratio showing up here. And I'll post some notes as well with some Fibonacci. But this is a kind of a basic one that's really, really amazing. Do you guys agree that it's just like awesome that if you add these 2 numbers, 6 plus 4, you're going to get 10? Right? And if you want to know the next combination, it's also. So let's think a little bit about this pattern. I'm going to write it down, okay? So let me kind of 3 plus 1 equals 4. So what was it? 3 plus 1 equal to 4. And if I go back to where it was, let me actually just copy and paste this. I just need to triangle itself. So I'm going to copy and paste the triangle. So what we want to understand is, why does this pattern show up? And you'll see the reason for it is extremely, extremely simple, but it requires just thinking about it. You know, it's not something maybe you would see right off the top of your head. But once you do see it, you'll be like, oh my gosh, that's really obvious. But we have to be careful in how we explain it. Okay, so let's look at this equation over here. 3 plus 1 equals 4. Lily, I didn't understand your question or your comment. Oh, why didn't he just use powers of 11? Oh, I see. Gotcha. Yeah, well, because you know what? This way, powers of 11 actually, you know, well, yeah. This way is very actually nice to go one row to row, because you just have to just add a bunch of numbers. So it's actually easy to compute. I think it's easier than powers of 11, because powers of 11, you got to carry stuff over. Okay, so I'm going to write this as a combination so that we can dig in and try to understand what it means. So can anyone tell me, this 3, which combination does it come from? I know it's just the number 3, but it actually came from a combination. And it's going to be really important to understand which one it came from. Can anyone tell me, in the way we usually set up Pascal's triangle in the expansion, which combination is this? So this is 3, choose 0. Nice. Isaiah, what did you say? Yeah, exactly. This is 3, choose 2, right? So I'm going to write it, instead of 3, choose 2, I'm going to make it look harder, but you'll see in a second it's going to make it nicer. This is 3, choose 2. And Isaiah, how about this one? Or anybody else? Where does this 1 come from? What combination is it really from? It's 3, choose 3. So 3, choose 2 plus 3, choose 3 is equal to, and what about this combination? Where does the 4 come from? Nice, Isaiah, excellent. And is everyone okay with the responses that Isaiah gave? Nice, 4, choose 3, excellent. That's where it came from. Okay, let's do it one more time. This time you guys will do it first. Can you explain this formula as combinations? So 6 plus 4 equals 10. We know that that's true, but what combinations do they stand for? So I'll give you guys a moment. Just tell me blank, choose blank. You know, you can do 4C3 or whatever you want. Just do it all in combinations. So the 6, the 4, and the 10. And we're gonna, the goal of this is try to understand where these numbers, why this pattern is happening, without really doing any math. Good catch, Lily. Angel, very close. Nice, good. Lily, do you want to share what you wrote?
So I got 4 choose 2 plus 4 choose 3 equals 5 choose 3.
Perfect. Plus 4 choose 3 equals 5 choose 3. Oh, okay. Very good. And as you guys, thumbs up if you understand, if you follow what I did here. Just kind of figured out the spacing and where they are, or how. Lily's answer here is really good. Excellent. Any questions? I'm happy to address any questions here. All we're doing is just kind of writing, we're observing the pattern that, oh, it seems to work, 6 plus 4 equals 10. And I'm just writing it, instead of doing 6 and 4 and 10, I'm just writing it as combinations. Any questions up to this point? Yeah, Diana, can you clarify which numbers you're referring to? Okay, these guys, the 4 choose 2 and the 4 choose 3? Okay, so the 6 and the 4, they came from the 4th row, right? Well, you know, the power, the row that corresponds to the 4th power of 4 expansion. And then you just start counting from here. This is 4 choose 0, 4 choose 1. This number comes from 4 choose 2. This is from 4 choose 3. And this is from 4 choose 4. So these two came from 4 choose 2 and 4 choose 3. That's why we got this one. And the 5th row, it's this number, right? So we just start here. 5 choose, you always start 5 choose 0, that's the 1. 5 choose 1, 5 choose 2, and then this one will be 5 choose 3. Okay. So what do you guys think is a general pattern for this rule? If I have two numbers next to each other in the nth row, so let's say I do n choose r minus 1 plus n choose r. I'm going to kind of move it down a little bit. This is a little bit abstract, but based on the pattern that we just did. So all this is saying is, if you notice what we're always adding is two numbers in the same row. That's why these numbers are the same. The 3 and the 3 are the same. The 4 and the 4 are the same. And the n are the same. And these numbers, one is less than the other. One is less than the other. What would the next number, what would this be equal to? Kind of in terms of symbols. Excellent. Angel, what did you write there?
N plus 1 choose R.
Excellent. N plus 1 choose R. So this is a little bit abstract. We don't need to worry about this too much. But this is the pattern. This is the formula for the pattern that we want to understand. This is the pattern that relates the two numbers above to the number below. Okay. Now let's step back a second and let's just think about this. And now I don't want you to think about, forget about this, 6, 4, and 10. I don't care about the actual numbers. Can anyone explain logic, using logic and using some sort of concept? Why, if you have 5 friends and you want to invite 3 of them, it's the same as 4 choose 3 plus 4 choose 2. Or maybe it will be better, yeah. Can anyone explain? Or let's do it with 100 friends. So if you have 100 friends, and let's say I'm going to do the formula. I want to invite 7 friends plus 100 friends, and I want to invite 8. According to this formula, this should be 101 choose 8. Can anyone justify why this is true? Can you explain it? Just take a moment to think about it. If I want to pick 8 friends out of 101, why can I do the thing on the left? I'll give you guys like 5 minutes to think. Just a few minutes here. It's a worthwhile problem. And any questions about what I'm asking? So without doing any math, just conceptually, can you give me a good argument why this number is the same as these two numbers? That's kind of the goal. And there's one really, really sort of straightforward way that once you see it, you'll be like, oh my gosh, that's. And you guys can find this. Any questions about what I'm asking? Anyone see the reasoning? Anyone see a way to explain this, to say it's true without doing any math? No numbers, no like arithmetic, no multiplication or division, nothing like that. Just thinking about inviting friends to the movie theater. That's all. That's all it is. Anay, very good. It does. This is the pattern exactly. I put these numbers exactly in the same pattern as the other ones. But now my goal is to say, why is the pattern true? To give an explanation of the pattern. So why do we know it's true? Without actually saying, oh, it's because of the pattern, because that's what we're trying to explain. And also without calculating these numbers, because that kind of would be a lot of work. Because the pattern should be true, we should be able to explain it without having to calculate every single time. Any volunteers? Any thoughts? Also, just you can share different ideas. If you might think you're somewhere there. Oh, nice, Conchita. Very, very good. I think you're really close. I think you basically got it. So can you refine that idea to explain why the left side is equal to the right side? Basically, like in this topic of counting, we sometimes are able to come up with an equation if we say the thing on the left is a different way of counting the thing on the right. But they're the same quantity. Like yeah, so that's kind of our goal. So, Kanji, you're really, really close. I think you basically got the main idea. So we'll wait a few more minutes because I think it's a worthwhile idea for you guys to think about. The question is, again, why is this true? Why is this true? And why is this true? Without doing any sort of arithmetic. Anyone have any ideas? Hit yes if you're totally stumped and you have no idea kind of where to start even. Okay, let me ask you this. Using friends in movie theater, are you comfortable with what this represents? Can you guys just message me or just hit yes if you're comfortable? With, in terms of friends in movie theaters, what does 101 choose 8 represent? Anyone want to just say what it is? Nice, Archer, what did you say there?
101 friends, only 8 can go with you.
Exactly. So you got to find the number of ways to pick 8 friends to go to the movie with you out of 101. Okay, how about on the left? What does this mean? Nice, Brandon. You want to just say what this one means in terms of friends and going to the movies?
You have 100 friends, and you choose 7 to go with you.
Perfect. And just to follow up, how about this one? This would be if you have 100 friends and you want to pick 8 of them. So why is it that if you have 101 friends and you want to count how many groups of 8 you can make, why is it okay to do this and then add up this number? And Kanjit, what did you say? What's your idea? And yes, go ahead. Kanjit, you want to share?
Because you get rid of one person, so that's why you have 101.
Oh, well, so we want 101, right? But let's say we have 100 people, we have 100 friends. We have 100 friends, and then we have one friend, let's call that friend Billy. Okay? Billy is friend 101. And here we have 100 friends. So, can you tell me the, Archer, yes, exactly. Archer, what are the types of groups you can make?
So it's basically just the fact that you have 2 different groups of 100.
Uh-huh.
So would it be?
Well, we're taking groups of size 8. So what are the types of groups we can make? If you invite your friends to go to the movie with you, and you have 101 friends, one of them is Billy, what are the types of groups you might encounter?
Billy with 7 other people just a lot of times.
Uh-huh. Right. That would be here, right? 100 choose 7. Yeah. Because you already have Billy guaranteed, and you got to pick 7 out of the 100 people. So you can either have groups with Billy, and then what about how many groups are there where Billy's not included? How do we find that? If we don't want to include Billy in our group, how many ways are there to do that? If we don't want to include Billy in our group, well, Billy's out of the group, right? Then we have to pick another group of 8, but there's 100 less. Sorry, there's one person less out of the things we're picking from. So there's 100 choose 8 groups without Billy. Mm-hmm. Exactly, 100 choose 8. Here, if I do, let me just maybe write it here. If I have Alice, Bob, Cindy, and Dan, I can say, okay, well, let me think about the number of groups that there are I want to pick a group of 3 friends. So there's groups that have Dan. That is this is the groups with Dan. So this is going to be Alice, Bob, Dan, Bob, Cindy, Dan, and then Alice, Cindy, Dan. Because I got to pick the one guy. I got to pick 2 out of these 3. And the last one is a group with no Dan. That would be Alice, Bob, and Cindy. So that's why there's overall 4 groups when you do 4 choose 3. Okay. What do you guys think? Now that you've seen it, is it a pretty simple idea? Why the pattern works? Somehow it's not obvious to see it, but once you kind of start thinking about things like this, you can get better at explaining these patterns. But I think it's really useful. Any questions about this? Anyone have a question to explain it?
Why is a group without Billy 100 choose 8 and not 100 choose 7?
Oh yes, because I'm interested on the right side of making groups of 8. So if Billy's not in my group, I still need to make a group of 8. In this case, Billy is in my group, so I'm only choosing 7 people. But here I still have 8 tickets to give away, and I'm not including Billy, so that's why it's 100. Angel, is that okay? Excellent. Yeah, that's a really good question. Spend some time thinking about this. I think it's a really nice idea. All right. I will give you guys just a challenge to try to do for homework. Do you guys remember the formulas that we did with combinations to express combination in terms of factorial? So I showed you guys that there's a formula, I think it was in one of the last classes, that you can just plug this in and do write everything in terms of permutations. So one challenge that is a really good exercise if you want a little more practice with permutations and combinations is actually to justify, to do this formula algebraically with permutations and get a common denominator to show that it works out. So this is going to be a homework challenge. It's not really any points, but it just kind of, I'll give you guys a chance to submit it just if you want to think about it, because I really think it's worthwhile to try to do this one. So homework challenge, just to do it algebraically. I don't think it's actually as insightful as understanding this concept. So the number of groups, 101 choose 8, is number of groups with that 101 first person, and the number of groups without. Okay, so I'm just going to briefly talk a little bit about the next concept. Let me see. Yeah, so I'll just introduce a little bit of the next concept, and we will, I would say 5 minutes. Yeah. So this will be more for next class. The next class is on and I think many of you have had some exposure to probability. So here's an example. Billy rolls a fair 6-sided die. What is the probability? What is the probability that he rolls 2 or greater? What do you guys think? Close. I think Gabby, very close. Read the condition carefully. He rolls 2 or greater. This is the requirement. So what are the outcomes that would satisfy that requirement? Nice, Gabby. Gabby, what do you say?
I put 5 out of 6.
Exactly. Yeah. And the way we think of it is, or how did you come up with, like, if you had to explain this to like a much younger student, why is it 5 out of 6? What do you explain? What's the idea here?
Okay, so there on a die there are 6 sides,
Mhm.
so that makes the denominator. And because you're looking for 2 or greater, you're including the 2, so it'd be, and then you add up all the 6-sided die, which adds up to 6. It'd be 5.
Yeah, that's right. So all the outcomes that are just bigger than 2. It's 2 or bigger. Sorry. So the denominator is the number of all possible outcomes, and the numerator is there are rules. You can get either the outcomes, the number of outcomes that satisfy the condition. And this is really number of all possible outcomes. And I'll stop here. We're going to continue kind of talking about this basic example. But it's essentially, hopefully you see from this is that probability is very, very closely related to the idea of counting things. And we spent a whole few weeks now counting different things. And now in probability, you have to count outcomes of some sort of process or experiment that either match a condition, and then probability just means take the outcomes that match the condition and divide in the denominator over all possible outcomes, the number of all possible outcomes. And so thinking about outcomes and conditions that those outcomes will satisfy, we'll introduce some language to talk about it, but that's really the underpinning of probability. It's really based on counting. You're counting something to find the numerator, and you're counting something to find the denominator. And that's it. All right, guys. Yeah, I'm going to post these notes. I'll assign some homework. It's really basic stuff on Khan Academy. So now, though, moving forward, the homework will be on Khan Academy. The challenge thing, I'll post a little comment for the challenge thing. It's not graded. If you just want to do it as for practice, I'll look over what you do and give you some feedback. I think that's really awesome. But yeah, I'll post the homework. It'll be due next week. And on Thursday, we will continue on with probability. I'll also post the notes ahead of time. So you guys, if you want to just look over the notes a little bit, it's really, I don't think you guys will have too much trouble with it. And those of you who I talked with, maybe if you feel still struggling with binomial expansion and stuff, let me know. I know it takes some time to get those concepts, but I strongly encourage you to just rewatch older videos and go through lectures until you feel like it clicks. And the last chapter, this last few weeks of material, it is kind of the most challenging stuff. So it is worth kind of spending some time on that. The rest of it you'll find should be considerably more straightforward. All right, guys, have a great rest of your day.
Thank you. Have a good day.
Bye, thank you.
Thank
Bye.
you.